Okay? So I want you to try that, which is simple applying the definition of Fourier transform and see. Okay, in next 5 minutes. Okay? And maybe the two theories to go around and chat with you and see what we have. Okay? So I want you to write down and do that practice, really practicing the manipulation of the Fourier transform. In class, right now. Okay. Now it is going to be equal to P of capital omega times x of s of capital omega times t. Okay. Who got this result? This is the time Fourier transform of this. So if you wish, from here, what I have is x of s small omega is equal to the summation in n of x n e minus j omega n. That's what I mean, right? And you know, that's just a function. I can change any variable I like. Okay. But everyone has that, right? Or majority. If not, you better check with your friend. In the frequency domain, I have the first guy. So if this one here go from this is a 1, then it's going to repeat itself like this, as you see. And here maybe, so if this one here, the pi over t, this pi over t would map into pi because we know the simple change, you know, the small omega equal to capital omega times t. This mapping from the continuous domain to the discrete domain. So we have that. And what I have here is the first term, which has k equal to 0, give you this red, yellow part here. But we have all the other alias terms going around. Okay? Now, in this formula, what I have is not x s omega, x capital omega times t. So I can redraw this term function here, right? Simply that before I have small omega and capital omega t here, so it just simply replay that like this. So let's go back to this. Okay? And now we want to have so now I ask you a question. What P should I use so that I can take this down and have this? The idea then pass filter, right? That is a clever answer because what I do need to have now is just simply a filter that throw away this component. So I need a filter that simply cut off this. Okay, so and that's okay. So here put it here. So put it here. To run out of space, so maybe I can write it on top here. So the idea reconstruction is I want to have a P of capital omega is the function that completely cut off and taking this part, because this part is what I originally had. Right? So that part here, it has to be equal to 0 when the capital omega less than, capital omega bigger than pi over t. So the p omega is the one that has to be equal to 0 here. How about inside here? What does it have to be? 1 over t. If this is a 1, I have 1 over t here, so that means I have 1 over t here. So what do I need to have in pt? I have pt, right? Because it's 1 over t, so I have this. Okay, so equal to t when omega, capital omega, less than or equal to pi over t. That is an ideal filter. And if I have this thing here, then what does it mean? in the time domain, what the function pt have to be? What the pt have to be? The same function, right? And here give us a simple exercise. You don't know if this is one, you can do the integral. Then the p of t ideally is equal to the sine of pi over t times t over pi over t times, big T over t. You can do an easy computation. And by taking this, you can plug in here, and it will allow you to get yt equals xt. Exactly. Okay, so that is the lesson. Any question on this? So, let me repeat here. The sampling theorems effectively have two parts. The first part telling you what happens when you go from the continuous domain to the analog, the discrete domain. And the second part telling you what should you do to bring back from the discrete domain to the continuous domain. Right? And these two things, it is really a cornerstone of DSP. So let me draw a diagram. Let me have a diagram here. And then we take a break. And it's known as the Shannon sampling theorem. And the condition that we have is that we have to sample them above the Nyquist rate. Is what the engineers have used all the time. The reason I wanted to get a little bit about this is because it is a simple just literally what Nyquist have, and the engineers for 70 years keep thinking about that. But if you have a signal that runs above Nyquist, you have trouble, right? The most cutting-edge resource today is actually people understand this very deeply and get deeper, and at certain condition you can do reconstruction way below the Nyquist rate. And that is one of the very advanced resource topics. And this afternoon we will have a famous professor, one of the leading researchers in DSP nowadays, Richard Barlow from Rice University, going to tell you about this cutting-edge research that it can do operate for certain type of signal below the Nyquist rate. So this afternoon we would have two very well-known DSP professors from Rice University coming in to give us the guest lecture, the cutting-edge research. That's why I tell you about sampling now. So you keep that background. So just before we take a break, you see the derivation I just showed you, it have a quite important implications. So what is important implications there? So that is a diagram we wanted to see. So you take the signal, maybe we go by the simple diagram first. You take a signal in the continuous domain, and you do the sampling operation here. So take the signal, do the sampling operations. So now it's something the computer can understand, right? And you can do all the DSP. So all the DSP algorithm will be running in this in this signal here. And then at the end of the day, after let's say you have 10 image, you download them to a computer, right? You have a digital image, and you can add also a digital effect, right? Or audio effect, right? So you know, like a lot of music now is making by audio effect, right? So record some sound and put it to the computer, add some drum, you know, some very special effect, and then you want to enjoy it, right? So then you can pump them out in the speaker here. So that's the D12. So the DSP happens here. But we need to understand the sampling is the first theorem, from here to here, and the D12 from here to here. Okay? And inside here. So understand the sampling is really understand the gateway inside DSP. Now, that particular theorem tells you something. First, because I have something, remember this behind here, some repetition like this. And that is good. And maybe the questions we would come up after the lecture, after the break, is a key formula that small omega discrete frequency is equal to capital omega times t. That really allow you to map, because yesterday, for example, if I expect something here, a certain frequency, now I digitize it, right? Put it in the computer, and in the computer will understand a different frequency. How can I really map out the real-time frequency into real-life frequency into a computer frequency? Okay, so let's take a break for now for 15 minutes, and we resume at 15. Some of this connection between